At no point in your rambling, incoherent response were you even close to anything that could be considered a rational thought. Everyone in this room is now dumber for having listened to it.
You lose! Good day, sir!
Welcome to CheMistakes. Here we go through actual student answers, why they're wrong, what can be done to improve them, and try and build an understanding through them. So here our question is, explain the following ionization energy comparisons. We have sodium, which has a first ionization energy of 496 kilojoules per mole, and chlorine, which has an ionization energy, first ionization energy of 1,251 kilojoules per mole. So the student response was, as you move across the periodic table from left to right, the ionization energy increases, which is why chlorine has a bigger ionization energy. Now that first statement is true, but it's lacking explanation. So it's really just kind of restating what we see from the data. It's saying this has a higher first ionization energy, and then the only explanation given is that as you move across the periodic table, the ionization energies go up. That is in fact the case. However, we want to get a little deeper into why that is the case. So the answer continues on. The atomic radius decreases across, so the electrons are closer to the nucleus, making it more difficult to remove them. Okay? That also is true. However, from a teacher perspective, this is explaining a trend using another trend. And that's generally frowned upon. So basically what we're saying here is, the student is saying here, is that the radius is decreasing as we move across, and therefore the electrons get closer, and therefore they're harder to remove. What we want to do instead of that is anytime we're explaining trends, we want to use three things to explain: effective nuclear charge, shielding, and principal quantum number or energy level. So if we're not using those three things to give an explanation, then we're probably not going to be looking at a situation where we're really communicating everything that we understand. Now, let's go ahead and look at these, and let's draw some Bohr model atoms of this. So we have sodium here with 11 protons and 11 electrons. There's our valence electron. And then we also have chlorine, which has 19 protons, 19 electrons. Okay, now our ionization energy data here is saying this. It's pretty easy to come along and take away this electron. It's only so much energy. But to take away one of these electrons is much, much more difficult. So we're trying to explain why that is the case. So if we go through our three factors here, we have effective nuclear charge, shielding, and principal quantum number. Well, N is 3 for both of these. So for both of our valence electrons here, we're looking at the same energy level for each one. So that's probably not going to be the differentiating factor between these two. If we look at shielding, one of the worst terms invented. So shielding here, we have how much repulsion do we have on this electron from all the other electrons. So the repulsion from electrons within the same energy level tends to balance because it mostly pushes to the left and to the right and not so much out. And so actually in chemistry we often ignore the repulsions from these and say they don't shield each other. That's not exactly true, but it's good enough for an introductory level of chemistry analysis. So we're going to ignore the shielding from all of these. We're going to look at these. This has 10 electrons shielding. This one right here. This one also has 10 electrons shielding. So we don't see any change from that. Now the last thing on here is effective nuclear charge. So effective nuclear charge is a combination of all the attraction and all the repulsion. So this has 19 protons attracting, it has 10 electrons repelling, so it has an effective nuclear charge of, I'm sorry, this is not 19, this is 17. Whoops. Let's try that again. So 17 protons attracting and 10 electrons repelling, so that would be an effective nuclear charge of +7. Over here, we have 11 protons attracting, 10 electrons repelling, so we have an effective nuclear charge of +1. So what we're seeing here is that really the reason why sodium has a lower ionization energy and chlorine has a higher ionization energy is that the amount of protons pulling on this electron is less than over here, but the electronic repulsion is mostly about the same. And so the combination of that, the effective nuclear charge, is much larger for the chlorine than it is for the sodium. And so an explanation that would be much better would be that the chlorine has a higher effective nuclear charge +7. Sodium has an effective nuclear charge of +1. And then maybe a brief explanation of what effective nuclear charge is. It's the combination of the proton pull and the electron repulsion into one term. So we're seeing a greater net pull from the protons since there are more protons and since the number of shielding electrons has not really changed by much. And therefore the ionization energy is higher for chlorine than sodium.
Okay, a simple wrong would have done just fine, but